Hi, I'll be talking about some recollections about when I discovered the factoring algorithm. But first, I thought we should go back and talk about where I was when this conference was being held. So when I was in 1981, I was a senior at Caltech, which is the same place Richard Feynman was. And so obviously, Feynman was preparing his keynote address when I was studying and getting ready to graduate. But I didn't hear anything about Feynman's keynote address or quantum computation. What I did hear from Feynman, there was a very interesting lecture that I went to called Negative Probability. And I'll mention it because first, he says a few things about negative probability in his keynote address. And second, I think it shows some, sheds some light on Feynman. So in this lecture, Feynman said that, he was been looking at Bell's theorem, and Bell's theorem is this proof that Bell had that shows that the EPR paradox is unavoidable, that really quantum mechanics cannot be local and realistic. I won't tell you what realistic means, but that disturbed a number of physicists, apparently including Feynman. So he looked very carefully over all the hypotheses that went into Bell's theorem to see if there were any hidden assumptions that he could look at, and he found one. The hidden assumption was that all probabilities were between 0 and 1. So he asked himself, suppose we let the probabilities be any real numbers, less than 0 or bigger than 1, and we arrange things so that only when you add up the probabilities to get the probability of some observable event, it has to be between 0 and 1. So this was his idea, and he hadn't worked it out when he gave the talk, and apparently he never worked it out because he published a paper a few years later called Negative Probability. And the very interesting thing about this paper was that this motivation for this negative probability work was absent from the paper. He didn't mention anything about Bell's theorem. He mentioned as motivation, well, is there any way we can avoid these infinities that appear in renormalization? And that that's another big paradox of quantum mechanics that nobody has done anything about. So I think this shows, that Feynman was really careful cultivating his mystique. He didn't mention the original motivation in the paper because, it would have been clear that he had been wrong about this and that he wasn't able to resolve the paradox of Bell's theorem. So he found another motivation for this work, which didn't destroy this Feynman mystique of never making mistakes. And there's another interesting thing about that, too. It shows that Feynman didn't take his own advice. In 1964, at a set of lectures at MIT, he said, "I'm going to tell you what nature behaves like. If you will simply admit that she does behave like this, you will find her a delightful, entrancing thing. But do not keep saying to yourself, if you can possibly avoid it, but how can it be like that? How can it be like that? Because you will get down the drain into a blind alley from which nobody has ever escaped. Nobody knows how it can be like that." But 15 years after he gave that lecture, he then disobeyed his words and started worrying about how could it be like that. And it was a blind alley, just like he predicted. Of course, maybe the advice he was giving wasn't to professors who were tenured, but for graduate students. I mean, the only graduate student I know about who did a lot of, had a successful thesis on the foundations of quantum mechanics and avoiding Bell's theorem is Hugh Everett, who proposed the many worlds theory in his graduate Ph.D. thesis. and he left academia after he graduated. So now I want to skip ahead to the next time. The first time I heard about quantum computing, it was a talk that Charlie Bennett gave at Bell Labs, and I don't remember the exact dates, but it was obviously after Bell's theorem in 1986, and I think it must have been, or not Bell's theorem, it was after BB84 in 1984, but it must have been before Charlie built his QKD apparatus in 1991, because I don't remember the apparatus from the talk at all. Anyway, Charlie gave the BB84 key distribution protocol, and he asked an open question, which was, is there any way of proving mathematically that this is secure? So I thought about it for a while, but I gave up because I was completely stumped at how you would take the BB84 quantum key distribution protocol and turn it into rigorous mathematics, which is rather ironic because, in 2000, John Preskill and I gave the first simple proof of the security of BB84. And of course, that was after we'd learned all about quantum information and quantum computation and quantum error correction, and all of the stuff we've learned went into that simple proof. Okay, so I gave up on worrying about proving the security of quantum key distribution, but then a few years later, in 1992, Thernsteinbazarani came to Bell Labs, and he gave his talk on Thernsteinbazarani, where he put quantum Turing machines into a mathematically rigorous framework, and where he had an algorithm for a contrived problem, the Thernsteinbazarani problem, which seemed to run faster on a quantum machine, Turing machine, than on a classical computer. So that really intrigued me, and I started thinking about whether there were any more useful or more convincing problems that could be done on a quantum computer much more efficiently than on a classical computer. I didn't get anywhere on this question until I saw a paper of Dan Simon's, and Simon was looking at this problem, find the period on the vertices of a high-dimensional cube. So here's a three-dimensional cube, in which case the problem is trivial, but if you have a 500-dimensional cube, it suddenly gets very hard. So there's a function on the vertices, and this function is the property that if you go into the screen and then move horizontally, you will see a vertex of the same color. So that means that these colors of the vertices are periodic, because if you add a binary vector to one of them, you will get another one of the same color. So Simon's problem was, given a function like this, which you only can access as an oracle, find the period. And the way he did this was by applying what is essentially a Fourier transform over a binary vector space. So I looked at Simon's problem, and I knew that Fourier transforms were very good at finding periodicity, and I knew that the discrete log problem was also very much related to periodicity, and the discrete log problem is one which, if you look at public key crypto systems, there are some public key crypto systems that the discrete log problem is the key to breaking it. If you could solve the discrete log problem, you could break the crypto systems. So a similar thing holds for factoring. If you can factor large numbers rapidly, you can break the RSA crypto system. But discrete log problem, you break the Diffie-Hellman crypto system, which is not as common, but which is still a very important problem. So I started looking at whether you could solve discrete log problem. And so for the discrete log problem, that looks very similar to Simon's problem. Now the function is not on a high-dimensional cube, but on a very large torus, and there's a period there. So in this example, if you move 2 vertices to the right and 1 vertex down, you see another vertex which is of the same color. And if you can find the period of this function on a large torus where you can only query the colors of the vertices by an oracle, you can solve discrete log. I knew that the Fourier transform was very important for finding periods, so I figured out how to take the Fourier transform on a quantum computer over exponentially large period, and then I figured out how to apply it to get discrete log. And there's a very embarrassing thing here, which is that I had seen Simon's paper when I was on the program committee for STOCK. So there's 2 big conferences in computer science, STOCK and FOX, and papers in those conferences are treated kind of the way physicists treat phys rev paper. The story, which I don't think is really true in either case, is that people count up the number of STOCK and FOX papers, and if you have enough of them, they give you tenure. Anyway, we rejected Simon's paper from the conference. And then, before it actually appeared, I realized I could use the idea to find, to come up with a discrete log and factoring algorithm. So I called Simon and, got him to send my paper, and so I would have a legitimate copy, and then I went and, wrote my paper. And Simon said that he never would have figured this out, so he didn't really mind that. But I, and at least I argued for accepting Simon's paper. I obviously didn't argue hard enough for it. I should have been jumping up and down and say, you absolutely have to take this paper. But I did argue for it, and I guess theoretical computer scientists didn't think highly of quantum computation, so it got rejected. Once I'd solved the discrete log problem, I gave a talk about it at Bell Labs. So before the talk, I'd only told a handful of people about it, including Jeff Ligarius, who found a very minor error and we fixed it, and my boss, David Johnson. But the talk was in Henry Landau Seminar, which is an internal seminar at Bell Labs, which has a very active audience. The speaker gets constantly pelted by questions, and there have been at least 1 or 2 occasions when people have never been able to get through more than the first 2 or 3 of their transparencies because they got so many questions they didn't manage to get anywhere in their talk. But actually it went very well. And then I went back to work and I managed to solve the factoring problem a few days later. And that weekend, so 5 days after my talk, I got a call from Thernsteinbazarani saying, I hear you can factor on a quantum computer. Tell me how it works. So there's a couple of interesting things. First, the rumor mill must have spread the result very rapidly. And second, if you know the old children's game of telephone, one person whispers something to the next, who whispers something to the next, who whispers something to the next, and it's completely changed by the time it gets around to the first person. Well, I had told everyone I'd solved discrete log, and I don't think I told anyone other than maybe 1 or 2 people that I'd been able to solve factoring as well, but somehow the rumor changed discrete log to factoring. Now, that's not too uncommon because there's an interesting relationship between the problems of discrete log and factoring. They can both be used to get public key crypto systems, and anytime anyone has ever found an algorithm for one of them, some time later, maybe 6 months, maybe a couple of years, the techniques from that algorithm can be used to apply to the other one. However, it's not the case that you can take any algorithm and with some kind of, stick it in some kind of machine and turn the crank and get an algorithm for discrete log out of an algorithm for factoring or vice versa. It's just that they are similar enough problems that one algorithm for one usually gives an algorithm for the other with enough thought. So yeah, when Umesh calls me, I told him that how to factor large numbers on a quantum computer. And the news spread very rapidly after that. So I think the first thing was there was, so Thernsteinbazarani was, called me on the phone. But the first time I talked about that with anybody was Charlie Bennett. There was a Columbia Theory Day, which was held twice a year in New York City, and there was one in late April. And Charlie Bennett and John Smolin and I arranged to get together at the Theory Day, and I could talk about the factoring algorithm to him, and then he explained some interesting things about quantum puzzles and quantum information to me. And so that's there. Then the next thing was I gave a conference at the Cornell Algorithmic Number Theory Symposium, which I think was the first of an annual conference. And I was invited at the last minute. This was the first few days in May. And so I flew up and gave my talk. And there was someone from the NSA there who came up and asked me questions about it afterwards. There was a conference at the Santa Fe Institute in mid-May, and I couldn't go, but Thernsteinbazarani talked about the factoring algorithm. And so a lot of people heard about it from there. And let's see. And that, I was deluged by requests for my paper. I got interviewed by a bunch of magazines, and I think the next big conference was a conference arranged by NIST in Gaithersburg, and that was in August. And it was specially arranged because of the factoring algorithm. And despite the fact that someone from the NSA asked me questions at the talk at Cornell, a lot of people from the NSA didn't know anything about or at least have told me they didn't know anything about the factoring result before the conference. And then after this, there was a conference in Torino that fall. There was a conference in Texas, which was the Physics and Computation Conference, which was sort of a follow-up to the 1981 Endicott House Conference. I think that was called PhysCop 94. And then there was Fox, which I had submitted my paper to, and both Simon's paper and my paper got accepted to Fox, and I presented the result there. So there was one big objection to quantum computation, and Rolf Landauer apparently already brought it up at the May conference at the Santa Fe Institute, which is that you cannot correct errors on a quantum computer, or at least it looked like you could not correct errors on a quantum computer. So why can't you? Well, it's basically there's the no cloning theorem. There are a bunch of techniques for dealing with faults on a digital computer. One of them is checkpointing, where you take your state of your computation and you write it down so if the computation gets derailed by an error after that point, you can go back to the checkpoint and you don't have to go back to the original thing. Another is error correcting codes, and error correcting codes introduce a few redundant bits. So if you make one error in the bits of a word in memory, you can use the redundant bits to fix it. And then finally, there's massive redundancy where you keep many copies of all your bits around and continually compare them and fix them by taking the majority. So it looked like none of these techniques could actually be used to correct errors on a quantum computer. I mean, checkpointing, what you do is you take your computation and you write the state of your computer down. That's making a copy. That's not allowed. For quantum error correcting codes, you take your bits that you have in memory and you make parity check bits, which are essentially redundant copies. So that also looked like it was no cloning, so that wasn't allowed either. And the final thing, massive redundancy. Well, if you have 5 copies of your computation running and one of them derails, now there's only 4. Now you want to take the 4 good copies and turn them into 5 good copies. That's cloning too. You're not allowed to take 4 copies of the quantum state and turn it into 5 copies because it violates the non-cloning theorem. So it looks like you cannot fix errors on a quantum computer. And if you can't fix errors, then you have to do your computation perfectly. And if you have, say, 1 billion steps in your computation, which is what you need to factor a, I guess, cryptographically important number, then you need to do each step in your computation accurate to 1 part in a billionth. And you ask experimental physicists, and they'll tell you that's absolutely impossible. So if you want to get an estimate for what the state of the art was, Jeff Kimball estimated that the techniques at the time could do 1 2-quantum bit gate with around 80% accuracy, which is pretty pathetic if you want to do 1 billion gates with 1 part in a billion accuracy for each of them. However, it turns out that quantum error correcting codes don't actually need to clone things. So the simplest classical error correcting code is you take 0 and you encode it by 0, 0, 0. You take 1 and you encode it by 1, 1, 1. And you can do that on quantum bits too. You can encode 0 by 0, 0, 0 and 1 by 1, 1, 1. And this is not cloning because if you take 0 plus 1, so a superposition of 0 and 1, you don't get 3 copies of the superposition. You get the superposition of the encoded 0 and the encoded 1. So this code corrects bit errors fine. So bit errors essentially behave the way that the bits in classical error correcting codes work, but it does not correct phase errors. If you make a phase error on 1 qubit, you actually make a phase error for the encoded qubit. So that means that phase errors are 3 times as likely, because if you have some rate of phase errors in your qubits, then the error rate in your logical qubits is 3 times as fast. Now, what I realized was that there's a transformation that takes bit errors to phase errors and phase errors to bit errors. So you can apply that transformation to the code, and now it will correct any phase errors, but bit errors are 3 times more likely. So what do we do? I mean, we have the errors. It looks like you can protect the bit errors, so squeeze the encoded qubit one way, but then the other kind of error becomes more likely. So is this something that's unavoidable, or can we fix this? Well, I realized that there's a 9-qubit code correcting any single qubit error, and it's formed just by taking these 2 codes and concatenating them. First, you encode using the phase error correcting code, and then you encode each qubit of the resulting 3-qubit code with the bit error correcting code. And you've encoded 1 qubit into 9 qubits, and it corrects any single qubit error. So sometime after I wrote this, and I've never, so it was too late to include this in my paper that gave the 9-qubit code, and I never bothered to publish it anywhere. I discovered that Perez had actually discovered the 3-qubit code that corrects bit errors much earlier. So in 1985, he wrote this paper called Reversible Logic and Quantum Computers. And in it, he started worrying about errors for quantum computers. And he proposed this 3-qubit code. And you can see that this 000 plus 111, except he calls them spin up and spin down, he's included this code. He didn't need to worry about correcting phase errors because he was just worried about doing classical computations on a quantum computer. And if you do classical computations on a quantum computer, phase errors don't matter. So Perez discovered the bit 3-qubit code that corrects bit errors and actually said some interesting things about it much earlier than my paper. After I wrote the 9-qubit paper, I started thinking about maybe there are better quantum error correcting codes. After all, the repetition code had been known for thousands of years classically, and nobody had invented the better error correcting codes until the 1950s. So I started thinking, well, there should be some more efficient quantum error correcting codes too, because we know one, but it's the analog of the very inefficient classical repetition code. So I started looking at repetition codes. Now the classical Hamming code encodes 4 bits into 7 bits and corrects 1 error, and this is probably the simplest classical error correcting code. It was discovered by Hamming around 1950. And well, you can do a quantum Hamming code too. And playing around with the classical Hamming code, I got the quantum Hamming code. And what this does is it encodes 1 qubit into 7 qubits and corrects 1 error. And you can see that it's just made by superimposing states of the classical Hamming code. So I showed this to Rob Calderbank, who was also at AT&T and was an expert on classical coding theory. And we generalized this to a whole class of codes you can construct, which were CSS codes. And Andrew Steen discovered the quantum Hamming code as well as this class at approximately the same time. And so they're now called CSS codes, after Steen and Calderbank and myself. So, inspired by this, a bunch of groups started investigating more complicated codes. So what they did was they put computers to work on trying to figure out codes, and 2 groups, one at IBM and one at Los Alamos, discovered a code that encodes 1 qubit into 5 qubits and corrects 1 error. And they actually discovered 2 different codes, but it was easy to see that they were just one could easily be transformed into another. And in fact, this is probably neither of them, but another a transformation that makes them look more symmetric. Anyway, I saw these papers and I said, well, there's obviously a lot of structure to the 5-qubit code because you can look at all the symmetries, and it has a ton of symmetries. So there must be some reason it exists, some way of systematically discovering it and describing it. So I started looking around that, and I wanted to figure out what the symmetry group of this code was. So I asked Neil Sloan, who was another mathematician working at Bell Labs, how would you find symmetry group of this code? So he said, well, you should use the program Magma, and he gave me example Magma program that he was working on a different problem, and he had just run to compute the group of symmetries of something else. So I put this code up on Magma and wrote a program. And it spit out the fact that the group was 5,160,960 elements in it. And this happened to be exactly the same number as Neil Sloan had found. So we looked at it more closely, and not only were they the same size group, they were the same group. And in fact, there was a deep connection between packings in Grassmannian space, which is what Niels Sloan was looking at, and quantum error correcting codes. And that gave us the hint to figure out how this code was constructed. It comes from additive codes over the field with 4 elements. And using this construction, we could find many, many, many more quantum codes. And this is, in fact, the theory of stabilizer codes, which were discovered and named by Dan Gottesman the same time that we had done our work. So I believe that's all I have time for. And thank you very much for listening. I'm very happy to have been part of this 40th anniversary celebration of the original Endicott House Conference on Physics and Computation. And I hope to enjoy the rest of it.